Somewhere in the darkness of space, there are places where time itself slows to a whisper and light can never escape. These enigmatic voids are known as black holes, celestial enigmas that warp our understanding of the cosmos and the nature of existence itself. Welcome to Let's Learn While You Sleep. As we embark on this journey into the essence of black holes, we will explore the vast realms of space, where the very fabric of time becomes malleable and gravity reigns supreme. With each moment, we will drift further into the depths of our universe, unraveling the mysteries of these extraordinary phenomena that challenge our understanding of physics and reality. As we delve deeper into the nature of black holes, it is important to first understand what they are. Black holes form from the remnants of massive stars after they have burned out their fuel and collapsed under the weight of their own gravity. During this stellar death, a supernova explosion occurs, scattering the star's outer layers into the cosmos, while the core implodes. The resulting gravitational pull is so immense that no matter, not even light, can escape its grasp. In fact, the defining feature of a black hole is its event horizon, the boundary beyond which nothing can return. Imagine standing at the edge of a dark abyss where the universe seems to fade into oblivion and time itself dilates. This phenomenon is not merely a figure of speech. The intense gravitational forces present at a black hole can stretch time. The stronger the gravitational field, the slower time passes relative to an outside observer. This concept, a consequence of Einstein's theory of general relativity, reveals that as one approaches a black hole, the flow of time will slow down drastically compared to that of a distant observer. If you were to watch a clock near the event horizon, it would tick faintly as you moved further away, creating a curious dissonance between your experience and that of faraway stars. This interaction between gravity and time creates fascinating paradoxes and challenges the very nature of reality itself. We find ourselves questioning not only the physical laws as we know them, but also our existence within this infinite cosmic tapestry. Every star, every planet, and every galaxy swirls in intricate dances governed by these unseen forces. As we consider the lives of these black holes, we can also ponder the fate of our own universe, where every moment is intertwined with the enigmatic depths of spacetime and the mysteries that lie beyond our understandings. Now, let us consider how black holes interact with their surroundings, creating phenomena that are both astonishing and beautiful. As matter spirals into a black hole, it forms a rotating disk known as an accretion disk. This disk is composed of gas, dust, and stellar remnants, gradually being consumed by the immense gravitational force of the black hole. As the material approaches this event horizon, it accelerates, subjecting itself to extreme temperatures of millions of degrees. This friction generates immense energy, emitting powerful X-ray radiation detectable by telescopes. Some of the brightest objects in our universe, known as X-ray binaries, occur when a black hole or neutron star pulls in matter from a companion star, creating an almost hypnotic light display around the black hole. Observing these celestial performances invites us to appreciate the sheer beauty and ferocity of nature at its most magnificent. While we speak of the power of black holes, we must also acknowledge the possibility that they are not mere ravenous voids, but rather gateways to entirely different realms of existence. Theoretical physicists contemplate the concept of wormholes, hypothetical passages through space-time that could connect two distant points, potentially enabling travel across the universe in the blink of an eye. This idea, though speculative, captivates our imagination and hints at the frontier of possibility that lies beyond the confines of human understanding. Some propose that these wormholes may be linked to black holes, creating bridges amongst the stars. Envision traversing the fabric of space-time, moving past the boundaries of our universe, and experiencing a reality where the rules of physics are rewritten. While scientific evidence for such phenomena remains elusive, the theory creates an ongoing dialogue amongst researchers, inviting curiosity and exploration into the unknown wonders of the cosmos. The mysteries of black holes represent not just the limits of our understanding of physics, but also an invitation to explore the very essence of existence itself. Let us now turn our attention to one of the most extraordinary consequences of a black hole's existence: the way it bends and distorts the very fabric of time itself. Einstein's general theory of relativity, published in 1915, revealed something profound about the universe we inhabit. Space and time are not separate, rigid stages upon which events unfold, but rather a single woven tapestry, a four-dimensional continuum that physicists call spacetime. And this fabric, remarkable as it may seem, can be curved, stretched, and warped by the presence of mass and energy. Near the surface of the Earth, this curvature is gentle, barely noticeable, and yet it is the very reason your body rests against whatever surface holds you now. Near a black hole, however, this curvature becomes extreme, almost beyond imagination. As you approach the event horizon, time itself begins to slow down relative to a distant observer. This effect is known as gravitational time dilation, and it is not a trick of perception, not an illusion or a metaphor. It is a measurable, confirmed prediction of general relativity, verified by experiments as precise as comparing atomic clocks at different altitudes on Earth. Imagine, if you will, a clock falling toward a black hole while you watch from a safe distance, far away in the quiet dark of space. As that clock drifts closer and closer to the event horizon, you would see its hands begin to slow, each tick stretching longer and longer, the seconds pulling apart like warm glass drawn thin. The light from the clock would shift toward the red end of the spectrum, growing dimmer and dimmer, a phenomenon called gravitational redshift. And at the very edge of the event horizon, from your distant vantage point, the clock would appear to freeze entirely, its final tick stretched across an eternity, the light fading to an imperceptible whisper. The clock does not stop in its own experience, of course. For the clock, for anything crossing that threshold, time continues to flow, moving inward, carried by the curvature of space-time into the interior of the black hole. And yet, to you, watching from far away, nothing ever quite crosses. It simply fades, reddening, dimming, dissolving into the dark like a candle flame seen through closing eyes. Now consider an even stranger question, one that pulls at the edges of what we understand. What happens inside a black hole, beyond the event horizon, in the place from which no light, no signal, no whisper of information can ever return? Once anything crosses the event horizon, the mathematics of general relativity tells us something deeply unsettling. The roles of space and time, in a sense, become interchanged. Outside a black hole, you have the freedom to move in any spatial direction, forward or backward, left or right, up or down, but you are compelled to move forward in time. Inside the event horizon, however, the curvature of space-time becomes so extreme that all directions in space point inward toward the center. Moving forward in time means moving deeper into the black hole. The singularity is no longer a place in space you might avoid. It becomes your future, as unavoidable as tomorrow. The singularity itself is the point at the very center where, according to classical general relativity, the curvature of space-time becomes infinite and density becomes infinite, and the known laws of physics cease to provide meaningful answers. It is important to say clearly that physicists do not believe the singularity is a true physical reality. Rather, it is understood as a signal that our current theories are incomplete, that general relativity, magnificent as it is, breaks down under these extreme conditions and must eventually be replaced or extended by a deeper theory, perhaps a theory of quantum gravity that unites the very large with the very small. Some researchers have proposed that quantum effects might prevent the formation of a true singularity, replacing it instead with a region of extraordinarily high but finite density. Others have speculated about connections to other regions of spacetime, the tantalizing idea of wormholes or bridges, though there is currently no observational evidence to support such structures existing in nature. What we can say with confidence is that the interior of a black hole remains one of the deepest mysteries in all of physics, a place where our most powerful theories reach their limits and fall silent. And there is a certain peace in that silence, in knowing that the universe still holds secrets so profound that even our greatest minds have yet to unwrap them, secrets waiting patiently in the dark. Let us step outward again, away from the crushing interior, and gaze upon something truly magnificent, the supermassive black holes that sit at the hearts of galaxies. Nearly every large galaxy in the observable universe, including our own Milky Way, is believed to harbor a supermassive black hole at its center. The one at the center of our galaxy is called Sagittarius A star, and it has a mass of roughly 4 million times that of our Sun, compressed into a region smaller than the orbit of Mercury. It was the patient work of astronomers Andrea Ghez and Reinhard Genzel, tracking the orbits of stars near the galactic center over many years, that confirmed the presence of this enormous hidden object. Their work earned them the Nobel Prize in Physics in 2020. And yet, Sagittarius A star is modest compared to the giants found in other galaxies. The supermassive black hole at the center of the galaxy, Messier 87, the very first black hole ever directly imaged by the Event Horizon Telescope collaboration in 2019, has a mass of approximately 6.5 billion solar masses. Try for a moment to hold that number in your mind. 6.5 billion times the mass of our Sun, gathered into a single dark heart around which an entire galaxy slowly turns. The event horizon of this black hole spans a diameter roughly the size of our entire solar system. Light itself takes many hours to cross from one side to the other. These supermassive black holes are not merely passive occupants of galactic centers. They play active and essential roles in the evolution of their host galaxies. When matter falls toward them, spiraling inward through vast accretion disks, heated to millions of degrees, the energy released can outshine the combined light of every star in the galaxy. These luminous phenomena are known as active galactic nuclei, and the most powerful among them are called quasars, visible across billions of light years, beacons from the earliest epochs of cosmic history. Scientists believe that the relationship between a supermassive black hole and its galaxy is one of mutual influence, each shaping the growth and character of the other across cosmic time. A slow gravitational conversation spanning billions of years. There is another kind of black hole worth lingering upon as you rest here in the quiet, one born not from the slow accumulation of matter over cosmic ages, but from the violent death of a massive star. These are stellar mass black holes, and they form through one of the most dramatic events in the universe, a core collapse supernova. When a star significantly more massive than our Sun, roughly 8 or more solar masses, exhausts the nuclear fuel in its core, it can no longer sustain the outward pressure that has held it in balance against gravity for millions of years. In an instant, cosmically speaking, the core collapses. The outer layers of the star are blasted outward in a supernova explosion, briefly shining with the luminosity of billions of stars, scattering heavy elements, carbon, oxygen, iron, gold, into the surrounding space, the very elements from which planets and living things are eventually made. If the remaining core is massive enough, generally believed to be above roughly 3 solar masses, a threshold known as the Tolman-Oppenheimer-Volkoff limit, then no known force in physics can halt the collapse. The matter falls inward, past the point of no return, and a new black hole is born. A stellar mass black hole, typically ranging from about 3 to perhaps several tens of solar masses. These black holes are scattered throughout our galaxy, millions of them drifting silently through the dark between the stars. Most are invisible, detectable only through their gravitational influence on nearby objects, or, in rare and beautiful cases, through the X-ray light emitted when they pull matter from a companion star. In 2015, the Laser Interferometer Gravitational Wave Observatory, known as LIGO, detected for the first time the gravitational waves produced by 2 stellar mass black holes spiraling together and merging, roughly 1.3 billion light-years away. The signal, lasting less than a second, confirmed a prediction Einstein had made a century earlier, that violent cosmic events would send ripples through the very fabric of spacetime. And so even in death, even in collapse and silence, the universe finds a way to send a message across unimaginable distances, a gentle tremor in the dark, arriving like a lullaby from the deep past. Let us now turn our attention to something that may seem impossible, and yet the mathematics insists upon it, the idea that black holes are not entirely black. In 1974, the physicist Stephen Hawking proposed something extraordinary, a discovery that married the laws of quantum mechanics with the curved spacetime of general relativity in a way no one had achieved before. He showed, through careful theoretical work, that black holes must emit a faint, ghostly radiation, a whisper of energy leaking from the very edge of the event horizon. This phenomenon, now known as Hawking radiation, arises from the ceaseless quantum fluctuations that fill even the emptiest reaches of space. In the quantum world, pairs of virtual particles are constantly appearing and vanishing, flickering into existence for the briefest of moments before annihilating one another. But near the event horizon of a black hole, something remarkable can happen. One particle of such a pair may fall inward, swallowed by the gravitational abyss, while its partner escapes outward into the cosmos, carrying with it a tiny measure of energy. From the perspective of a distant observer, the black hole has just radiated a particle, and in doing so, it has lost an infinitesimally small amount of its mass. Over unimaginable stretches of time, far longer than the current age of the universe, this process would cause even the most massive black holes to slowly, gently evaporate. A stellar mass black hole would require roughly 10 to the power of 67 years to fully dissolve, a number so vast that the word eternity scarcely does it justice. And yet, the universe is patient beyond all human reckoning. This radiation is extraordinarily faint, far too dim for any current instrument to detect directly, which is why Hawking radiation remains a theoretical prediction rather than an observed phenomenon. But its implications are profound, for it suggests that black holes are not eternal monuments. They are temporary structures, born in violence and destined, in the fullness of time, to fade into nothingness, leaving behind only the faintest trace of thermal radiation scattered across a cooling, darkening cosmos. Even the most fearsome objects in nature, it seems, must eventually yield to the quiet passage of time. Consider now what happens to the information that falls into a black hole, for this question has ignited one of the deepest debates in modern physics, a puzzle that has occupied some of the finest minds of our era for nearly 5 decades. When a star collapses, when gas and dust spiral inward past the event horizon, all the intricate details of that matter, its composition, its quantum states, the particular arrangement of every particle, seem to vanish from the observable universe. And yet, one of the most fundamental principles of quantum mechanics holds that information can never truly be destroyed. It can be scrambled, rearranged, encoded in ways almost impossibly difficult to recover, but it must, in principle, always persist somewhere. This tension between the apparent information-destroying nature of black holes and the information-preserving laws of quantum theory became known as the black hole information paradox, and for years it divided physicists into opposing camps. Hawking himself initially argued that the information was genuinely lost, that black holes represented a fundamental exception to quantum law. Others, including the physicist Leonard Susskind, insisted that the information must survive, encoded perhaps on the surface of the event horizon, in a manner consistent with a concept known as the holographic principle. This principle suggests, remarkably, that all the information contained within a volume of space can be described by data encoded on its boundary, much as a hologram encodes a three-dimensional image on a flat surface. In 2004, Hawking famously conceded the argument, acknowledging that information is likely preserved, though the precise mechanism remains an area of active research. Some current approaches suggest that subtle quantum correlations in the Hawking radiation itself carry the information outward, slowly and delicately, as the black hole evaporates. Others propose that the interior geometry of the black hole is far more complex than classical physics would suggest. The full resolution remains one of science's great open questions, a place where gravity and quantum theory meet and refuse to speak the same language, and where the answer, when it finally comes, may reshape our understanding of reality itself. Now let your thoughts drift to the center of our own galaxy, where something truly immense resides in patient, ancient stillness. It is called Sagittarius A star, a supermassive black hole sitting approximately 26,000 light-years from Earth, nestled at the very heart of the Milky Way. Its mass is roughly 4 million times that of our Sun, compressed into a region smaller than the orbit of Mercury. For decades, astronomers inferred its presence indirectly, watching the stars nearest to the galactic center trace swift, elegant orbits around an invisible point of tremendous gravitational influence. Two teams of researchers, led by Andrea Ghez and Reinhard Genzel, spent years meticulously tracking these stellar motions, and their work was so precise, so beautifully conclusive, that it earned both scientists the Nobel Prize in Physics in 2020. They demonstrated that stars near the galactic center move at speeds of thousands of kilometers per second, whipping around their hidden companion in orbits that could only be explained by the presence of an extraordinarily compact, massive object. And then, in May of 2022, the Event Horizon Telescope collaboration revealed the first image of Sagittarius A star itself, a glowing ring of superheated gas surrounding a dark central shadow, the telltale silhouette of a black hole's event horizon as seen from across the galaxy. The image was constructed not by a single telescope, but by linking radio observatories across the globe into a virtual instrument the size of the Earth, a feat of coordination and computation that took years to refine. What you would see in that image is not the black hole itself, of course, for nothing escapes from within. You see the light bent and gathered around its perimeter, the last photons tracing their desperate arcs before vanishing forever. It is a quiet portrait of immensity, this dark circle at the center of everything we know. And it has been there for billions of years, silently anchoring the slow, majestic rotation of hundreds of billions of stars, including the one that warms your face each morning and lights the world where you now rest. And so we come to one of the most haunting questions that black holes pose to the human imagination. What would it actually feel like to fall into one? Let us picture it together, gently, as a thought experiment, a journey you need never take except in the safe theater of the mind. If you were to drift toward a supermassive black hole, one millions or billions of times the mass of our Sun, the crossing of the event horizon would be, by all accounts, remarkably gentle. Because the black hole is so vast, the tidal forces near its horizon, the difference in gravitational pull between your head and your feet, would be negligibly small. You might not notice the moment of crossing at all. There would be no wall, no barrier, no flash of light to mark the boundary. The stars behind you would blue shift and brighten, the universe outside compressing into an ever-narrowing circle of light above. But the transition itself would be as seamless as drifting from shallow water into deep. And yet, from that moment forward, every possible path through space-time would lead inward. Not because some force is pulling you, but because the geometry of space itself has curved so completely that the singularity is no longer a place in space. It is a moment in your future, as unavoidable as tomorrow. For a smaller black hole, however, the experience would be dramatically different. The tidal forces would be ferocious, stretching your body along the direction of fall and compressing it from the sides, a process physicists have given the whimsical name of spaghettification. Long before you reach the event horizon, you would be drawn into an impossibly thin thread of matter. But in either case, from the perspective of a distant observer watching you fall, something astonishing would occur. They would never see you cross the horizon. Your image would linger there, growing ever dimmer, ever more redshifted, frozen at the edge of time, a fading ghost suspended at the boundary between the knowable universe and the unknowable darkness within. To them, you would hover there forever, a last whisper of light at the threshold of silence. Let us now turn our attention to a phenomenon so strange, so beautifully counterintuitive, that it seems to belong more to poetry than to physics, and yet it emerges directly from the mathematics of general relativity. It is called Hawking radiation, and it was first proposed by the theoretical physicist Stephen Hawking in 1974, in a paper that quietly shook the foundations of our understanding of the universe. Imagine the emptiness of space near a black hole's event horizon, that invisible boundary we have spoken of, where the grip of gravity becomes absolute. Even in the apparent vacuum of space, quantum mechanics tells us that pairs of particles are constantly flickering into existence, a particle and its antiparticle appearing together for the briefest of moments before annihilating one another and vanishing back into nothingness. This process happens everywhere in the universe, a ceaseless quantum foam bubbling beneath the surface of reality. But near the event horizon of a black hole, something remarkable can occur. One particle of the pair may fall inward, crossing that threshold of no return, while the other escapes into the cosmos, carrying with it a tiny amount of energy. To a distant observer, it would appear as though the black hole itself were radiating, glowing faintly with a warmth so slight that it would be immeasurably small for any black hole we have yet observed. And here is where the idea becomes truly astonishing. Because the escaping particle carries energy away, the black hole must lose a corresponding amount of mass, for mass and energy are equivalent, as Einstein's famous equation reminds us. Over incomprehensibly vast stretches of time, far longer than the current age of the universe, this process could cause a black hole to slowly shrink, to grow warmer as it diminishes, radiating more and more intensely, until, current theory suggests, it would eventually evaporate entirely, vanishing in a final whisper of light. The largest black holes, those supermassive giants at the hearts of galaxies, would take perhaps 10 to the power of 100 years to fade away, a number so large that writing it out would fill pages with zeros. And so even these eternal-seeming monuments to gravity are, in the fullness of time, impermanent, dissolving slowly back into the fabric of spacetime from which they were born. So, as you settle deeper into the quiet of this moment, consider the strangest collaboration in all of modern physics, the meeting place where gravity and quantum mechanics attempt to speak to one another, and where black holes serve as the great mediator. For much of the 20th century, these two pillars of physics, general relativity and quantum mechanics, have stood apart, each spectacularly successful in its own domain, and yet seemingly incompatible when brought together. General relativity describes the universe at its grandest scales, the curvature of spacetime around stars and galaxies, the expansion of the cosmos itself. Quantum mechanics governs the smallest scales, the behavior of atoms and subatomic particles, a realm of probability and uncertainty. For most situations, there is no conflict, because the domains do not overlap. But inside a black hole, at that mysterious point called the singularity, both theories must apply simultaneously, and here they collapse into contradiction. The density becomes infinite, space-time curves without limit, and the equations that have served us so faithfully simply break down, returning answers of infinity that physicists interpret not as truth, but as a sign that our understanding remains incomplete. Some researchers propose that a theory of quantum gravity, a framework that unifies these two great pillars, might reveal that the singularity does not truly exist, that matter falling inward reaches some extraordinary but finite state, rather than an infinitely small point. String theory offers one possible path forward, suggesting that the fundamental constituents of nature are not point-like particles, but tiny vibrating loops of energy, whose behavior might smooth away the infinities that plague our current models. Loop quantum gravity offers another approach, proposing that spacetime itself has a granular structure at the smallest scales, a quantum foam that prevents the infinite compression a classical singularity would require. Neither framework has yet been confirmed by experiment, and this remains one of the great open frontiers of human knowledge. But it is beautiful, is it not, that these dark and silent objects, these places where light itself is captured, may hold the key to the next great revolution in our understanding of reality, waiting patiently at the edge of everything we know. As we draw our exploration of black holes to a gentle close, let us reflect on the beauty and complexity of the universe that surrounds us. The poets may have sung about the stars, and the scientists may seek to chart their timelines, yet in the end, we weave our stories through the fabric of space. Each black hole reminds us of the mysteries that lie ahead, echoing the eternal dance of light and darkness, of understanding and wonder. With every breath, we find ourselves nestled within this cosmic symphony, transported by the allure of the unknown. Allow your mind to drift, to surrender to the silence of the night, and find peace within the embrace of darkness. Thank you for spending your night with Let's Learn While You Sleep. Subscribe and come back tomorrow night. We'll be here. Sleep well.